So let's talk about different types of solutions and how we're going to get to those solutions. So there's a bunch of different types when we are dealing with differential equations. So there's three common ways that we can represent a function. The first way is algebraically, which is using a formula for the function, probably the more common way that you are used to seeing functions being represented throughout the levels of math you've already been through. The second way to represent a function is numerically. This kind of brings you back to like the beginning stages of math when you first started being introduced to algebra in like an elementary algebra class. You were showed x and y pairs and you put them in a t-chart with an x and y. So that was a numerical representation of the function. Table representing the inputs and outputs. This probably was so basic back then that you may not have actually recognized that that was a legit way to represent a function. But when we're working with differential equations and the fact that differential equations has not only x and y variables, but it also has their derivatives and multiple possible forms of their derivatives, a numerical table is helpful when representing a function in certain applications. And the third way to represent a function is graphically. So graphically and algebraically were probably two of the more prominent forms throughout your algebra courses. And graphically kind of paired with numerically, because in order to graph a function, a lot of times you most likely put a table together in order to plot the points to graph the function. But graphing out functions of inputs and outputs is a visual way of representing a function. So let's discuss the algebraic approach first. There are two types of solutions for the algebraic approach. There's an explicit and an implicit. So the explicit solution to a differential equation or initial value problem, commonly abbreviated IVP, is an algebraic representation of the solution to the differential equation or the initial value problem, written in terms of elementary functions, where the dependent variable is written explicitly in terms of the independent variable. So you can see here at the bottom that an implicit solution, the independent and the dependent variables are wherever they would like to be, while the explicit is specifically solved for the dependent variable and the function is written in terms of the independent. So most of our solving in the future, we will get to the implicit, and in some cases, we'll be asked to put it in the explicit form, but that's not always possible, which is why we're defining both. In many cases, solving for y is actually impossible without technology, and in some cases just impossible altogether, especially when there's different levels of y. So if there's y squared, y cubed, all in the same problem, all in the same solution, then we know that that's not a possible formula that we can solve for one variable. So in many cases, implicit is our only way of identifying the solution, or writing the solution rather, but we do try to write it explicitly as we are used to working with functions that are solved for a particular variable in many cases. A numerical approach is going to be Euler's method. So Euler's method was actually introduced in, I believe, Calc 2. So you've most likely already heard of this, although it really depends on your professor, because a lot of things that were taught in prereq courses to differential equations, because they're taught in differential equations when there's snow days or issues or, COVID hits, those topics are usually the first to go because all the professors know you're going to see it again in another course. So those of you who have not seen Euler's method before, no problem. I'm going to teach it to you as if you've never learned it before anyway. So for Euler's method is based off of three observations. The solution to the IVP is a function which has a graph that goes through the initial point, x naught, y naught. The second observation is that y prime is the slope of the tangent line, which you should recall from Calc 1. You spent a good first third of the course in Calc 1 learning about the derivative And essentially you're learning about the slope of the tangent line that turned into the derivative, which covered the next third of the course. So 2/3 of Calc 1 was solely focused on the derivative or the slope of the tangent line. And the third observation is that f of xy gives a formula for the slope of the tangent line at any point xy on the graph. So if you recall from Calc 1, you can find the formula for the slope of the tangent line that you can then find the actual slope given a specific point on the function, giving you a numerical slope versus a formula. So terminology clarification, again, I have no idea what the gaps in your math are. Some of you may have years in between these courses, and therefore I can't assume that these are fresh in your mind. And even if you took Calc 1 and Calc 2 in the last 2 semesters, we still forget things over a 3-month summer and a 1-month winter. So let's just run through some things. This is very similar to physics. So you've seen this in math and science at this point, where when you have a variable x naught, y naught, those are indicating an initial point. So for us, in an initial value problem, our initial point is not always 0, 0. It depends on where the function is defined to be starting, and depending on the application and what makes sense in the application of where it should start. Y prime, you should be very familiar with, is representing the derivative, aka the slope of the tangent line. So if you recall, if we graphed the basic parabola x squared and we wanted to find the derivative or the slope of the tangent line, to find the formula for any slope to any tangent line to this parabola x squared, we would do a simple power rule. We'd bring the 2 down in front, come back up and subtract 1. I like to think of it as a counterclockwise circle. Whoop. And that gives us the formula for any slope of any tangent line to this parabola being 2 times the x value of the point that you'd like the tangent line to go through. So if we're taking a look at the point x equals 1 on this parabola, well, we would put 1 into the derivative. We would say, oh, the slope of the tangent line at the point 1 on the parabola x squared has a slope of 2, which means it goes up 2 over 1. This notation, this function notation, you guys are used to seeing f of x and f of y separately, which indicate that it is a function in terms of x for f of x and a function in terms of y for f of y. You can see that here, that the only variable written on the other side of the equal sign is a y when you have a single variable in the function notation. But when you have 2 variables, it just means that the function is written in both variables. So just want to make sure that that's clear of the difference between f of x, f of y, and f of xy. Now let's recall another topic, linearization. This one, again, is a hit or miss on whether you've seen it before. It was introduced in Calc 1, but it is one of the first topics to usually get deleted if there are any issues with the schedule or whatever it might be. Snow days aren't necessarily an issue in the last year, but COVID-related restrictions could have caused the schedule to be slimmed. And therefore, you may or may not have seen this particular formula before. But let's go through it step by step because it directly relates to Euler's method. So linearization is a small section that was introduced in Calc 1. And then Euler's method was using linearization in Calc 2. Again, both of those may not have been touched upon depending on your professor or time or crazy situations. And so we are going to cover it as if you haven't seen it. So here, it's essentially, this whole crazy looking formula is really just talking about what you learned in the beginning of Calc 1, which is taking a step closer and closer and closer to the point, finding slopes of tangent lines in order to estimate the slope of one specific tangent line. So if you recall, it was finding the slopes of what's the other name of secant line? Whew, almost escaped me. You were finding a bunch of slopes of secant lines, which are average velocity, in order to estimate the slope of the tangent line, which is a very specific velocity happening at a very specific moment. And we use the slopes of the secant lines to estimate the tangent line before we learned how to find an actual derivative. And that's exactly what Euler's method is really doing. It is following a pattern and getting you closer and closer to a specific point in order to make an approximation. So given a differential equation, okay, so y prime is equal to some function in terms of both x and y, and an initial value condition, so some initial x and some initial y, you're going to calculate some points until you get to the desired ending. Okay, so maybe I want to know, I'm going to start at 1, 1, and I want to know what's happening at 3, 4. Well, then I'm going to have to calculate each step along the way in order to get to my desired end. So we're going to follow this formula, which absolutely makes no sense when you first see it until you start seeing an example. And h is a step size. So n is a count and h is a step size. So that step size is constant throughout one problem, and it is usually picked for you, so you don't have to choose that. It's a very small number because, again, the larger the step size, the bigger the average is, and the less accurate we're working in. The smaller the step size away from the point, the more accurate we are when we are estimating. So we are going to follow these steps to our desired point. So we start with an initial point to find the first y. To find the second y, we use the first y instead of the initial point. And you see how we just keep swapping out. The previous result is going to be filled into the function to find the next result. So you can't skip any steps. You have to keep going through the process because each next step is using the previous solutions. So let's try one together. Let's consider the initial value problem. Y prime is equal to 0.1 times the square root of y plus 0.4 times x squared, with an initial point to start at being y of 2 equals 4, or the point 24. We want to use Euler's method to obtain an approximation at 2.3 using a step size of 0.1. So that means we will have to do 2.1, 2.2 before we can get to 2.3. So notice I'm stepping up the x value by 0.1 every step that we take. Let me actually make this smaller so I can stay right here in the PowerPoint. I'm going to do this out with you. So just giving myself some more room. Doop. Let's put this down to size. Actually, we can just delete this because it'll still be there when you guys pull up the PowerPoint. Okay, giving myself more room now. Let me put this back up. Let's do this problem out together. So the first thing we want to look at here is the fact that we have the function in front of us, we have the initial point, and we have the step size. So what we want to do is we want to start with the formula. You know what, let me write the formula in front of us so that we have it in front and I can refer to it. You are finding the next y value. Remember, n is let's say it's 0, so we're finding y1 because 0 plus 1 is 1. By using the previous y, adding it to the function we are given solved with the previous point values, and multiply that output by the step size h. Okay, so let's see what that actually looks like when we do it out. So if we are trying to find, let's label our initial point, x naught, y naught, is the 0.24. So we're trying to find y1. Now, y1, again, is 0 plus 1. So when we are looking at y1, that means yn is y0. So I'm going to write this out with letters first, and then we'll put the numbers in. So we are going to calculate y1 by using the initial y plus the function here solved for x naught and y naught. So we would be doing 0.1, let me put this in brackets, times the square root of the initial y value plus 0.4 times the initial x value squared. And then we multiply by the step size after we complete that calculation, which our step size was given to us as 0.1. Okay, so that's what we're doing. We're taking the initial y's and the initial x's, substituting them into our formula here. And that's going to give us the next y value. So y1, notice that what we're calculating here are approximations at a specific points of a solution we don't have, by the way. Because this y prime is the differential equation. So we don't have the solution, so we're trying to approximate certain values with a solution we don't know, and that's what Euler method is doing for us. So y naught is 4 plus 0.1, and again, I'm going to put this in brackets so I remember I'm doing a multiplication at the end. Square root of 4 plus 0.4 times 2 squared, all multiplied by 0.1. Okay, so I would put this in my calculator, making sure to remember order of operations, or using the brackets that I have here, the calculator would do this just fine. And we get that y1 comes out to be 4.18. Now, in some cases, when you see that the y values are coming out to all the same values, let's say we do this and all of them are coming out to 4.18, that just means you're over rounding. So if you don't want the values to be the same, if there are more decimal places. So that just means go out farther, have 4 decimal places, 6 decimal places, so that you can see what the change is from the points. So now we just write our x1, y1, let's label. Now, y1 we know is 4.18, but we just have to really think about what we're doing to figure out what the x is. So remember, the step value is how far we're moving in the x direction. So that means if we started at 2 and we're moving at a 0.1 step, then our x1 was 2.1. So that's not actually calculated. That is just using the, well, I guess it is calculated using the step, but it's not a formula. You just add your step to your previous x. So now that we have a new point, x1, y1, we look to see what our desired end is, and we see that it was 2.3. So we're not done yet. We have to keep going until our x value is 2.3, and then our answer is whatever the y is that's paired. So now we need to find y2. All right, so y2, we're going to take y1, which is 4.18, and add to it the function 0.1 times the square root of y1, 4.18, plus 0.4 times the x1 squared, and we multiply that function by the step size of 0.1. When we do that all out, our y2 comes out to be 4.3768. So now we have a x2, y2, where we add another 0.1 to 2.1, giving us 2.2, and our y value paired is 4.3768. Again, we see that the x value is not 2.3 yet. We still have one more step to go. So we do our last step. We find y3 by using y2 and x2. So we have 4.3768 plus the function evaluated, 0.1 times the square root of 4.3768. plus 0.4 there we go, times the x value of 2.2 squared, all multiplied by our step size of 0.1. That gives us a y3 value of 4.5914. So we just found that x3, which is 2.3, and y3, which is 4.5914, 5914. And this is our answer. That is our approximation of the output of the solution that we don't know with an x value of 2.3. Now, in these next couple slides, you will see that I've given you the step-by-step instructions on how to do Euler's method in your calculator if you have an 89. For the homework on this section and for the first exam where this is on, you have to do everything out by hand. I want to see that you understand the function and understand all the parts and how to use it. So this is really just to help you check your answers, and you can use your calculator after the first exam. So typically new stuff, I want to see that you can do it out by hand and understand everything thoroughly. And then your calculator is more than happy to aid you. So you can read through these slides on your own. I don't really need to walk them through, especially since I don't have a way to project my 89 onto this recording without switching to a completely different format. So just walk through those with screenshots. You should be able to follow that with no problem. The TI-89 guide PDF version is also posted in our Blackboard course, which is where I got this from. I just screenshotted it, so you can find it there too. The last approach, the geometrical approach, we are talking about slope fields. So this is a very tedious, long process, and our TI-89 also draws slope fields for us, which we will be using again after this homework and after the first exam. But it's really great to use your calculator in order to check your answers and make sure that you are on the right track. So the basic steps for drawing a slope field is you have to choose a rectangular piece of the coordinate plane. Typically we stick around the origin because it really doesn't matter where you're drawing, but if you focus on the origin, you can do like a 2x2 space. At each point in the array, you calculate the slope using the function, and you write these little tick marks that represent the slope of the solution at that specific point. Then, once you have all these little points, all these little lines, then you take you use the channels between the lines in order to draw the curves that best fit, which then you are drawing approximate solutions graphically without, again, having a formula for the solution. So notice that the algebraic approach is actually solving the differential equation and finding the actual formula of your solution. The numerical approach is estimating the result of a solution that you don't know what the formula is, but you're using Euler's method to find outputs. And the graphical approach is finding what your solutions approximately look like without, again, having the actual formula to draw it exactly. So let me show you another example show you an example of slope fields here. So if we are given the differential equation y prime is equal to xy, and we wanted to draw the slope field, let's follow these steps. So the first thing we want to do is choose a point. You know what, I got to do this in another color than black. So we choose a point. Step 1, choose a point. Again, I like to stick with the basic center of with the origin. So I'm just going to choose a point 1, 1. And again, we're going to have to choose many points, but we choose a point, and then the second step would be to find the slope with at that point. So find m. That's supposed to be an n, but that turned out to be an m. Hold on, fixing. Find m. So to do that, we know that y prime is m. So we are finding the slope. M is the same thing as y prime. And it says that the formula is x times y. So our x is 1 and our y is 1. So we are essentially just calculating 1 times 1, giving us a slope at 1, 1 to be 1. So the third step would then be to draw that slope at that point. So if this is our origin here, smack dab in the center. So picture this, the x-axis, and this is the y-axis. Then 1, 1 is right here. And a slope of 1, 1 is up 1 over 1. So if I visualize this is the place that I am drawing a line segment to, I just draw a little tick mark that if I was to draw the whole line, it would be a slope of a line with 1, 1, but we don't want to draw all the way through. We want just the tick mark. Okay? Let me erase this little star. So now I have a little guidance in this one area. I know that when I draw near here, I have a slope of 1. So now let's continue to do that for all the points in the surrounding area. And the easiest way to do that is to create a chart. So if I create a chart, okay, and I put the x's up here and my y's over here, let's do -2, -1, 1, and 2, -2, -1, 1, and 2. And you can picture that we're going to map these out. So 1, 1, we already know the slope is 1. And if this was an actual table, it'd be easier for you to see. So let me try to draw a quick table for you. There we go. Okay, so we know one of the slopes, and again, we used 0.11 in order to graph the tiny little line segment with a slope of 1, and we continue to find the rest of these slopes. So let's do that. So now, let me erase this area because this will be my calculation area. Okay. All right, so let's do -2, -2. So we have y prime is equal to -2 times -2, which gives us +4. So we place in here, the slope is +4 at -2, -2. So we find that point, -2, -2, and I need a slope of 4. So I count up 4 over 1. So I'm visualizing this point right here, and I kind of draw a line that points or is in the direction of my goal, this star thing. Okay, so now let's do y prime is equal to, let's move up, we'll just go left to right in the first row. So we have -1, it doesn't really matter the order in which I write these because they're being multiplied. -1 times -2 is +2. So -1 on the x, -2 is here, and we have a +2 slope. So I'm really focused on the origin when I'm drawing this. Again, I'm drawing the line as it's a target through the origin. So you can see the different slopes, the differences between these line segments, because this has a slope of 4 and this one has a slope of 2. Okay, let's do the point +1, -2. So we have y prime is equal to +1 times -2, which gives us a -2 slope. So +1, -2, whoops, erase that line, that wasn't supposed to happen. +1, -2 is here, and we are doing a -2 slope, which means you go down 2 over 1. So that would be, I have to guesstimate because it's kind of off my graph, but I'm visualizing it's about here. I don't think I need to write out the math every time. I think you guys are getting the point on the math because it's just simple multiplication. So 2 times -2 is -4. So 2 -2 has a -4 slope, which will be quite steeper. Notice that these are estimations, so you don't have to feel like they have to be perfect. They just have to be a guesstimate. -2 and -1 gives us +2, -2 and 1 gives us -2, -2 and +2 gives us -4. I'm just going to fill out the chart real quick since it's simple multiplication. -1 and -1 is +1, -1 and +1 is -1, -1 and 2 is -2. 1 and -1, -1, 1 and 2 is 2. 2 and -1 is -2, 2 and 1 is 2, 2 and 2 is 4. All right, so now let's finish writing all these dots in. So we have -2, -1, and there's a slope of 2, so up 2 over 1. I'm kind of focused on this corner here. There we go. -1 and -1. The slope is 1, so I'm going to focus on the origin. Then we have 1 and -1. Come on. There we go. 1 and -1 gives us a -1 slope. Oops, that has to go the other way. That was a +1 slope. Oh, and so are these. I did these backwards. These are both positive as well, and they were supposed to be negative. So let me fix that. So down here, +1, -2 was a -2 slope. So that should be down 2 over, oh yeah, I definitely went the wrong way on that. This one should be steeper. Okay, sorry about that. Those are negative, so those should be facing the other direction. We were on -1, -1. 1, -1. Here is a -1 slope, so that goes this way. Then we have 2, -1, that's this point, and we have -2 slope. So again, I pick a point to focus on. If I go up 2 and to the left, that'll also help. So there's my -2. Again, all guesstimation is just to give you an idea. I didn't do any of the zeros, which I really should have, so I'm going to have to do those after. But anything that has a 0 is going to have a 0 slope. So when it comes to either the x or the y being 0, one of them being 0, 0 times anything is 0, and a slope of a 0 is a straight horizontal line, which means all of these points along the axis are going to have a horizontal slope. Which is helpful. Next row, -2 and 1. -2. We must have already, oh, up here, -2 and 1. Got a little lost there. That is a -2 slope, so that's going to be here. -1 and 1, which is this point here, has a -1 slope. And then we have 1 and 1, which we already did, and 2 and 1, which is a 2 slope, +2 slope. Last row, -2 and +2, we have a -4 slope. So a bit steeper. -1 and +2, we have a -2 slope, so a little less steep. And then we have +1 and +2, which has a +2 slope, and 2, 2, which has a +4 slope. Okay, so this is our slope field. And given this slope field, we then can guesstimate what does the solution look like. Now, what's important is to really see that these are almost like a barricade. They're all horizontal lines. And we use these to guide our solutions. So one possible solution it looks like would be a parabola, okay? A family of parabolas. And usually that's the case, is that these are families of parabolas, not just a single solution. You usually have a family of curves that make the solution. So I can see that these is one possible solution here, following the guidance of the little slopes. Again, you don't have to worry about me marking these right or wrong when it comes to guesstimating. I'm looking to see that you did the work and that you somewhat understand how to draw the lines. If your lines are not 100% correct, that's okay, because we're guesstimating, we're learning, and these are all estimations anyway. So in order to really get an accurate read, we'd really have to do a much larger slope field. But for our purposes, since we're doing this out by hand right now, I'll stick to a 2x2 frame because you guys will get the point at least at there. And you won't be super overwhelmed with a ton of calculations because some of the functions are not going to be as easy as just multiplying the x times y. And therefore, they're going to take a little longer to come up with all of these. All right, well, those are the three different types of solutions that we can, or ways to find solutions for differential equations: algebraic, numerically, and graphically.